My name is John Horgan. I am a science journalist. I teach at Stevens Institute of Technology, and I have been a kind of science correspondent for Blogging Heads TV for, 15 years or so. And now I have my own little fiefdom called Mind-Body Problems, which I interpret pretty loosely. We're all over the place. So today, I'm going to have a conversation about quantum mechanics with one of the world's leading philosophers of physics, Tim Maudlin. So, Tim, thanks for showing up.
Well, glad to be here. No problem.
So first, I always like to get a little background and find out from people why they're doing what they're doing. So can you just say how you ended up as a philosopher of physics?
Sure. When I was undergraduate, I was bouncing around between philosophy classes and physics classes and classics and stuff because I had interests in all of them. And in the case of physics and philosophy, they just conceptually go together in a very natural way because if you keep asking this, pestilential question, why is that? Or, explain that, give me the foundation of that. What lies underneath that in a certain direction that takes you to philosophy. And in another direction, in a particular way, it takes you among the sciences to physics. Now, you have to be very careful about that latter point because people say, biology is just applied chemistry and chemistry is just applied physics. And that's false. It's just not true that understanding physics gives you all the same insight that you get out of studying chemistry or biology or computer science and so on. But there is a sense in which it is true that every biological system is a chemical one and every chemical system is a physical one, but not the other way around. And so if you have a certain kind of curiosity that pushes always down, that'll lead you to philosophy, it'll lead you to physics. So I ended up actually doing my PhD in history and philosophy of science, kind of specializing in philosophy of physics, which was just a natural fit. And then got a job in a philosophy department because no physics department will hire somebody with this background.
So the way you just described the sort of the way explanations go, how, you're going deeper and deeper, that reminds me of how Steve Weinberg has described physics and the quest for a unified theory, that if you keep, you've got an explanation at one level and you say, well, why is that? Why do we have, the genetic code or something? And then that'll take you deeper and deeper. And Weinberg, this was in Dreams of a Final Theory, and he said that sooner or later, you're going to get down to this ultimate level of explanation. And that he was hoping would be this unified theory. This was back in the 90s when it looked like that might be possible. A lot of serious people thought it would be possible. And we're talking about string theory and those sorts of things. I'm sort of jumping the gun here a little bit.
Well, can I just make a comment about that, which is, yeah. I disagree with a way of understanding what Weinberg is claiming there. I don't think that going down these levels that we're talking about always leads you to a better or deeper or more revealing explanation. An example I always like to give is suppose on my desk there's a physical object and it's producing light, okay? And it's producing light in a certain pattern, which happens to be a little colored wheel that's doing this, right? That's spinning. And I call a physicist in and I say, look, can you tell me how long that's going to go on, right? And the physicist, we imagine this kind of super physicist who just analyzes the thing as a physical object and says, okay, I can now, applying physics to its physical description, tell you that that will go on for exactly 2 years, 3 months, 4 days, 5 hours and 3 seconds, and then it'll go blank, okay? And if you say, how do you know that? And you say, well, here's the initial description, and here's the Schrodinger equation, and blah, 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 right? And you say, okay, thank you, physicist. And then you call in the computer scientist, who doesn't look at the damn box at all. He looks at these papers that are beside it. And he says, look, your program has a loop in it, right? Step 10 is go to step 20, and step 20 is go to, step 10. That little thing's going to spin forever. Now, he's wrong when he says it'll spin forever, because after that many years, the computer's going to break. I mean, that's what the physicists can figure out, is that the computer will burn out. But on the other hand, he's given me a hell of a lot more understanding in a certain way about what's going on, understanding that the physicists might never get. So I don't think that these are levels of always better explanations. But on the other hand, if the physicist makes the prediction it'll stop, and the computer scientist says it'll spin forever, because that indicates it's going in a loop. No, the physicist is really right? His prediction is going to be correct. But he's not giving me the same understanding. So that part I disagree with. Now, what I think Weinberg really wanted was not to reduce all the other sciences to physics, but just to make sure there was a physics where all the physics fit together in a coherent way. And of course, that must be true, because physics does actually work, right? I mean, somehow or other, nature figures out how to do electromagnetism and weak nuclear forces and strong nuclear forces and gravity all at the same time. So a completed physics should have a theory that does them all at the same time in a coherent way. That's what a unified, ultimate physical theory would look like. And sure, I think there must be such a thing. I mean, I hope we can find it.
Yeah. So what you just said reminded me of, and that's a great case study for, the perils of reductionism. It reminds me of this essay that another Nobel laureate in physics, Phil Anderson, wrote in the 70s. Phil Anderson sort of was like a thorn in the side of the particle physicists. Mm-hmm. He kept sticking up for the profundity and the beauty of condensed matter physics. And so in this little essay, More is Different, he basically is saying what I think you just said, which is that you've got all these different levels of reality that we experience as humans and as living creatures. And it's absurd to think that there is some kind of optimal way of understanding everything. We've got to have theories that are sort of appropriate for the level that you're looking at.
Right.
Which is kind of an obvious thing, but it seems to be forgotten sometimes by certain kinds of intellectuals.
Yeah, I mean, I would say Foundations of Physics has made some progress in that regard in the last couple decades. Because when I was, a sprout, you were told there were two main pillars of physics. One was relativity, which was giving you space-time, and the other was quantum theory, which was sort of dealing with matter. And now the standard line is, well, there are three main pillars of physics: relativity, quantum theory, and statistical physics. Okay. Now, statistical physics isn't introducing a new kind of thing. It's rather talking about the sort of understanding you can have of complex systems with many parts, where you can actually, instead of having to go down and describe them in complete detail, you can get a lot of understanding at a much higher abstract level. So it's a different kind of thing, but everybody, I think, better appreciates that a lot of just everyday physics relies inevitably upon statistical methods, and you have to think hard about statistical explanation, statistical understanding. And I think that fits with some of the things Anderson would have said.
Okay, so now I've got a lot of ground to cover. I basically wanted to talk about this book. By the way, Tim, I have to say, I think you could have come up with a catchier title for this.
Well, the history behind that was that this is in a series, okay? And it was very constrained how long it could be. And I agreed to write, idiotically, philosophy of physics.
Yeah.
And I started writing Space-Time, and I realized I wasn't done and I'd used up all my pages. So I went and begged that they could let me do 2 volumes. Okay. And so it became Philosophy of Physics, Space and Time. And then the other one was supposed to be Quantum Theory, actually, and Statistical Theory. And then I started to write the second one. I didn't have room for Statistical Theory, and they said, do not come back and ask us for a 3rd volume. But maybe one day I will actually write that as well.
Well, see, I thought you were being deliberately forbidding, like, there's no.
I had no choice in the matter. I like the titles I have complete control over are quite different, and also the cover art. I don't like the cover art very much. If you look at my other books, it's much nicer.
It's pretty grim, but the book is fascinating. So I've been not just reading it, but I've been kind of studying it. I like to write notes on the blank pages at the beginning, so then I can just look at that quickly and say, oh yeah, that's where he was talking about the GRW interpretation. So I wanted to ask you some questions about this. So it seems to me your premise, your mission, and I guess this is true of all your philosophy of physics, is to try to create out of physics, out of these highly mathematical models that we have to explain stuff going on in the world, to relate those to some kind of intelligible worldview, which starts with saying, what's out there? What does the world consist of? What are the things in it? And then how do they end up doing what they're doing?
Yep.
Right? And this book is dealing with this big problem posed by quantum mechanics, which of all our physical theories is the one that is the least intelligible. And there are some people who have even sort of thrown up their hands, going back to the beginning of quantum mechanics, and have said, listen, this is kind of it for the whole project of trying to make sense of reality. But this theory works really well, so we should be content with that. And you're saying basically, fuck that. No, we've got to try to relate this mathematical model to the world.
Well, what I'm saying is in a way more radical than you're suggesting, and also more commonsensical than maybe it sounds. So if you go back and read Newton's Principia, Newton does things the right way. He sort of starts at the beginning and says, look, I have some basic things I'm going to take for granted are part of the world. Space, right? Time, motion, matter, various properties of matter, mass, forces. And he's very clear at the beginning, and he says, here's what I mean by these terms, and there's a big scholium on space and time. Here's what I mean by space and what I mean by time and what I'm committed to. And only when all of that's set does he then write down the laws of motion, because the laws of motion involve space and time. If you haven't explicated what you have in mind, I don't even know what you're talking about, right?
Yeah.
And that's the way it should be for all of physics, right? That you can't write down a piece of mathematics and have it mean anything physical without the terms in it referring to something, and you want to tell me what you're talking about. And the problem with quantum theory is that it wasn't developed that way. It wasn't developed first with the postulation, look, here's what we think there is in the world. Like, imagine in electromagnetic theory, when people came along with the idea of a field, which was kind of a novel idea, and there was a bit of fight about whether they should take it seriously or not, but at least they understood, okay, I'm telling you there are these fields, and fields are different than, particles, and here's what they're like. And now let me write down some equations about them, right? The problem with quantum theory is that you just had some equations and then some rules of thumb about how to use them to make predictions, but you didn't have what I call a physical theory, which would clearly articulate what you're committing yourself to as existing in the world. So, and the problem is physicists just got used to not having that. and then forgot that's what physics was all about. And so, some of us are saying, no, right? I didn't go into physics to learn how to predict things. I'm not actually all that interested in predicting things. I went into physics to try and understand things. And the ability to predict just isn't the ability to understand.
It seems to me that the paradox with quantum mechanics is that you get enormous power. These equations, whatever, they give you the ability to manipulate nature and to invent stuff. Right. Lasers and modern transistors and integrated circuits are based on things that about the behavior of atoms and electrons and so forth. And now we're building quantum computers. So I think it's fair to say that most physicists don't give a damn about the meaning of the theory, and given that they can do so much with it. So it's this weird, you'd think that power and understanding would be intertwined, but when it comes to quantum mechanics, they seem to have diverged sharply.
Right, but it's not just quantum mechanics. I mean, if you go back to Kepler's laws, right? I mean, there's this big step forward in astronomy and understanding the solar system when Kepler said, look, stop trying to do it in terms of circular motion, uniform circular motion, and use ellipses instead. And not only that, not uniform motion around ellipses, but this motion where you sweep out equal areas in equal times. So Kepler writes down these laws, and then he has 3 laws, and those are really powerful for making predictions, right? But Kepler didn't attempt to give an account of why you should be using them. And if all you wanted to do is predict where Mars is going to be, that's fine. But Newton came along, and for example, the equal area law, Newton gives an explanation, a really beautiful, very simple explanation in terms of his fundamental mechanics, that for any central force, like the force of gravity that's pointed at the sun, if that's operating, you're going to sweep out equal areas in equal times. And anybody can understand that argument. And that, you say, oh, now I understand why Kepler's laws hold, right? And every physicist would have recognized that and did recognize that as a huge step forward. The funny thing is, physicists, kind of the stereotype is they look down on engineers, but then they turn around and say, well, I'm just a glorified engineer and all I care about is building stuff, right?
Yeah. Well, it's interesting the way you're describing the sort of classical physics is, I guess, you've got this theory that it sort of works. It makes predictions. It's useful. But then it leads to the understanding, which I'm assuming then leads to more useful predictions and applications and all that. So there's this kind of fruitful interplay between the power side of the science and the understanding side of the science. It just seems like when it comes to modern physics, and especially quantum mechanics, that interplay has sort of broken down to a certain extent. I don't know. And yeah. you're trying to fix that. Anyways,
because the understanding part was given up. I mean, every physicist, and it wasn't philosophers who made this up, but every physicist who says the attitude is shut up and calculate, what that's saying is it literally don't try and understand it, right? You're avoid asking obvious questions like what the hell is going on here, okay? And that's to me, that's renouncing what physics is about.
Yeah.
I would have never gone into physics if, in the first physics class I ever got in classical mechanics or in electromagnetism, they just said, don't try and think about what's going on, right? Just run some math. That's boring. I mean, why should I spend my time doing that? What do I get out of that?
I'm a science journalist for the same reason. I mean, it seemed to me that what made science exciting back in the 80s when I became a science journalist was that there were some scientists who were saying, hey, we're gonna explain this whole thing. We're going to understand reality.
Yeah, and look, the language they used is the language I want. Like I have real problems with string theory, but when a string theory, the first thing they say to you is, look, on my theory, electrons that you thought of as little point things, they're really strings that vibrate. And in fact, the difference between an electron and a quark is how it vibrates, right? That is an attempt to make comprehensible a fundamental postulate about what there is in the world. Not how do I calculate something, not what's the math. This is what there really is. I mean, I may never understand the math, but if that turned out to be correct, just grasping that, oh, really, all there are little strings that vibrate, right? It would give you some deep insight.
Yeah. Well, okay. That's a whole nother discussion.
If it were true.
I want to get to, I want to get to your book, and I guess I'll try to ease us into it by asking you what you think is the central dilemma for quantum mechanics. What's everybody talks about its weirdness, the paradoxes of quantum mechanics. What to you lies at the heart of the strangeness? What's the hardest thing to explain, to make intelligible?
Well, I think there are certain things that people have touted as very incomprehensible about quantum theory, like so-called wave-particle duality, right? That's what you hear all the time, or the double-slit experiment, for example. People always use the two-slit experiment. In principle, that behavior is not at all hard to understand. And once made a comment, all these people at the time arguing wave or particle, why didn't it occur to them wave and particle, right? Why how do I explain that there's both particle-like behavior and wave-like behavior? Because there's a particle and also there's a wave, okay? And that's one way to understand what's going on. And if you take that way, the double-slit experiment is just what you'd expect, and you understand what's going on, everything's perfectly clear. Now, we don't know that way of understanding it is correct, but if you take that route, you certainly know what you're talking about, and there are no paradoxes, and everything just falls out. The one thing that quantum theory has, that all the different approaches have, is this thing that's called the wave function, or I call the quantum state. And it's a non-classical thing. It's a funny kind of global thing. And you have to get a little used to it. And it's surprising, and it has really surprising results, not just in the double-slit experiment, but more so in violations of Bell's inequality. And those ought to shock your classical conscience, because they're very unclassical, but not incomprehensible. It's just a different kind of thing. The way that introducing fields into physics, okay, this is a different kind of thing, right? Democritus had atoms in the void, and he didn't have electric fields, right? Democritus wouldn't recognize electric fields as either atoms or void. And so it takes a little while to get used to that. Understand that suggestion, get used to it. So you need to get used to the quantum state, because it's this global kind of holistic thing. And once you do that, then there are details about exactly how the theory, well, there are different proposals for what the fundamental ontology, basic postulates of the theory ought to be. And then but as soon as you understand what they all are, then you have a normal discussion between competing ideas.
When you talk about the wave function being something that's sort of global, I'm assuming that you're alluding to entanglement and non-locality. And maybe the first thing you can do for me is explain. So I have sort of used them and understood those terms, non-locality and entanglement, interchangeably. Mm-hmm. So is that right or wrong, or can you? It's
on the right track, but it's not quite right. I should mention here, Schrödinger said in the paper when he talks about the cat that he introduced the term entanglement in that paper. And he says that it's entanglement that forces a departure from classical lines of thought. So not indeterminism, not wave-particle duality, entanglement. Not every entangled state would lead to a violation of locality. But where there are violations of locality, they always arise from entangled states. So that's why they're not quite interchangeable, but they're very, very, if it weren't for entanglement, you wouldn't have non-locality. You can have entanglement without non-locality, but if it weren't for entanglement, you wouldn't have non-locality. So that's really where the heart of it comes from.
So you can have local forms of entanglement.
Right. I mean, I can give you a kind of funny example. In a single atom, or even in a single particle, it has a kind of degree of freedom that corresponds to its position, and a different one that corresponds to its spin. And those two can be entangled just for a single particle. Mm-hmm. Its position and its spin can be entangled. Now, that's not going to give rise to any non-locality because you only have one particle. And to get non-locality, you have to be doing experiments on two objects that are separated.
Right.
So entanglement is a broader concept than non-locality.
Okay. All right. Thanks. I appreciate that. By the way, as I think you know, because we've had some exchanges on Facebook and elsewhere, I am trying to learn quantum mechanics over the last, 8 or 10 months or so. And I've learned a little, gone back and brushed up on calculus. I've tried to learn linear algebra for the first time and, Braz and Ketz and all that. And I'm like a case study, and a little knowledge is a dangerous thing. And I've just recently realized, or maybe incorrectly realized, that entanglement is kind of a special form of superposition. So a superposition being this uniquely, actually, I don't even know if it's uniquely quantum, but it's an ability of a particular object or thing being described by quantum mechanics to be in different states at the same time, but it's in this kind of limbo.
Okay, let me start. I mean, what you're saying is what a million people would say. It's just technically not even correct. And if you're really trying to understand, this is a good place to get cleared up, because a million people will tell you the wrong thing.
Okay.
Superposition, the way people talk about superposition is just completely wrong. You have a set of possible physical states. You have it in any theory, right? For Newtonian mechanics, possible physical states of your system. In electromagnetic theory, here are the possible physical states of your system. In quantum mechanics, the possible states, the quantum states, the states of the wave function, form a vector space. That's just a mathematical fact. Mm-hmm. And we're all familiar, the standard example of a vector space is where you have arrows, like in 2 dimensions, and to add them, you lie them head to tail and, draw in that one. We all know kind of how vectors work with vector addition and vector subtraction, right? Well, that's all superposition is. If you're dealing with a vector space, to say that this state superposed with that state yields this state is just to say you're dealing with vectors. Just add this vector to this vector, and you get another vector. Mm-hmm. And if every vector is a physical space, then every vector is a superposition of other vectors in infinitely many ways. So, think I just have a little arrow that runs from here to here. Well, I can think of that as this one plus that one, or this one plus that one, or that one plus this one, right? I can add up other pairs of arrows in infinitely many ways, and that's true of all of them. So you can't, as it were, pick out a state and say, oh, that state's a superposition, and this state isn't. They're all superpositions. They're not all entangled.
Right.
So here's where entanglement, no, you give me a state, it's either entangled or it isn't.
All right.
And that's objective about it. I mean, if you give me a state of a system thought of as decomposed into 2 subsystems, and it's either an entangled state or it isn't. And that's just a fact about it. Some are and some aren't.
So this kind of, this understanding that I'm trying to express to you comes from this book called Q is for Quantum by Terry Rudolph. who's a quantum theorist, is now trying to start a quantum computing company, and he's got this formalism for describing certain quantum effects that's really simplified, and he says that the important thing to know about quantum superposition, because apparently there are versions of superposition even in classical physics. At least that's what I'd say.
Electromagnetic theory works the same way. Take two possible electromagnetic fields. You can always superpose them, which just means add them up. And get a third one.
And they also exhibit interference and things like that?
Yeah, that's standard way that you understood light interference.
Okay.
In Young's theory, the reason why people went to the wave theory of light was because they saw interference effects in light. And the obvious way to understand that is to use a wave theory. And in wave theories, typically you can just superpose solutions to get other solutions.
All right. So now my understanding is crumbling even more, because I had thought what Rudolph said is that quantum superposition, you get these states where the superpositions can cancel each other out.
Oh,
right?
But that's true in standard. So people knew about interference bands with two-slit light, just with light.
Mm-hmm.
And of course, you get cancellation there too. That is, it's a funny thing. You block one of the slits, and you'll get some light here. You block the other slit, you'll get some light here. You open both the slits, you get no light there. Now that sounds a little funny, but that's how just water waves, the standard two-slit water wave experiments. You have constructive and destructive interference.
Well, so then
destructive interference means with only one I get some, with only the other I get some, but with both I don't, because they destructively interfere. And that's just by adding them up.
So, all right, then let me take another shot at this.
Okay.
The quantum superposition happens at the level of not of things happening in the real world. So, real waves canceling each other out. It's the cancellation happens. Oops, sorry. Happens at the level of probability, so that you get the wave function is saying that this state has this probability of being, instantiated when you measure it, and that and then you've got this other thing, this other state that's part of the superposition that is the negative of that first state, and they cancel each other out.
Okay, so can I again?
I'm worried that I'm just digging myself deeper.
No, it's fine. You're asking good questions. I honestly want you to understand, because it's not that hard.
Okay.
But again, people say things that can be very confusing.
Yeah.
So we're fundamentally dealing with this thing called the wave function. People sometimes call it a probability wave, but it isn't. When they're careful, they call it a probability amplitude.
Right.
And they call it an amplitude because you have to square it to get a probability. And that's really important.
Yeah.
Because you never get destructive interference between probabilities, because probabilities are always positive. Yeah. So they can't knock each other out, right? They can add up, but they can't knock each other out. But something that can be both positive and negative, like in a vector space, you've always got a vector going this way and the opposite vector going that way. And when you add them up, this is just part of the definition of a vector space, you can get zero. Right. Vectors can always destructively interfere. So the wave function is a probability amplitude, which is why it can exhibit destructive interference. You just, if I add up one like this with one like that, they add up to nothing.
Yeah.
And then if I square this, I get something positive. If I square this, I get something positive. But if I square the sum, I get zero. So that's all that's going on. The interference is going on in a straightforward way, just like with water waves, at the level of the wave function, that is at the level of the probability amplitude.
Yeah.
And then you have to square that to actually get the probabilities.
All right. Now, the reason I brought up superposition is that I was just trying to get to my understanding of entanglement as a special case, a superposition in which you can't. You've got two different things that are in superpositions and that are combining into one superposed state, and you can't resolve those into more, I don't know, elementary superposed states.
Okay.
I think
again,
I'm
you're in the area. Let me just walk you right up to the goal here. I now have a system that has two parts, and it's easy to think of these. If you want to understand why this is so puzzling, imagine the parts are spatially separated from each other. So I literally have one part of it's in this room and the other part of it's in the other room, okay? And now you say, all right, this system that has these two parts, what kind of physical states can it be in? Well, take the parts individually. Take the part in this room and imagine there's some set of states I can prepare this thing in, yeah? And there's some other set of states I can prepare the other one in. And then just from that, I get what are called the product states, and that's just what you'd expect. So I prepare this one in state A, I prepare that one in state B. Or I prepare this one in state A, and I prepare that one in state A. All of those product states exist. They're things you'd be shocked if they didn't exist. I mean, if I can do this with this part and do that with that part, then the whole thing is described by that. Those are the product states. What you might also think is that that's all the states there are. The only way to prepare this system is to prepare it in a product state. That's what's not true, okay? So there are the product states, which are like that, and then there are the entangled states. And an entangled state cannot be written as a product state. It is a superposition of product states, okay? Right. So I'll say that one more time, because this is where superposition comes in. Entangled states are superpositions of product states, right? But they are not themselves product states,
right?
Right. So in cases of spin, I can prepare my system like this. That is, this particle has spin up, this particle has spin down. That's a product state. I can prepare it like this, where the spins have been switched. That's another product state. But then I can do something really clever and surprising, which is superpose those so that it's, as it were, 1 over root 2 this plus 1 over root 2 that. That's an entangled state. And I can't understand that in terms of just a particular state here and a particular state there. It's not a product state. I can't specify what's going on with this one without talking about the other one. That's the kind of holism. That's the kind of, and you can see how non-locality is going to get into this, because I can't even talk about the state of this particle without bringing in the state of one that's very far away.
Yeah,
that's non-classical. That's weird. I
think you just explained more clearly what my understanding was. So I just want to say that the takeaway for me is that superposition, you've got all these different things that people say are part of the core mysteries of quantum mechanics. You've already talked about complementarity. You think that's sort of overrated. To me, it seems that you can sort of focus on entanglement and say that in explaining entanglement, you're going to explain superposition, or maybe the other way around. So maybe there's you can think of them as both at the core of what makes quantum mechanics so hard to understand.
Yeah, I mean, as I say, that was Schrodinger's view, and I think he was right on target when he said it. He said, look, this entanglement thing, which is that you can have a system with two spatially separated parts that can't be understood by describing this part on its own and then this part on its own. Yeah. And then saying the whole thing is just, as it were, the logical sum of those two. That doesn't happen in classical mechanics. That doesn't happen. I've talked about electromagnetic theory. That doesn't happen in electromagnetic theory, right? If I have an electromagnetic field, I can talk about what it is over here and what it is over here. And what it is in both places is just the sum, the logical sum of what it is here plus what it is here. But with entanglement, you can't do that. And that's what Schrodinger pointed out. And you're not ready for that. Okay, that's the thing you got to get your head around. That there can be non-product states, even when the parts of the system are separated from each other, arbitrarily far apart. I mean, there's a famous letter of Einstein to Bohr, where Einstein very clearly states his own supposition, which is that if I take any little piece of space, I should be able to say what's going on there completely independently of what's going on anywhere else.
Yeah.
Right? And that's what entanglement denies.
Right.
That's what was so spooky. That's the source of the spookiness of quantum mechanics that Einstein didn't like.
All right. So, we've already been talking for a while. I had all these questions that I wanted to ask you about the different major models of quantum mechanics or interpretations. But I know that you were also thinking of giving us a little explanation of Bell's theorem, Bell's inequality.
Yeah, I mean, it would actually fit right now if you want to do it. I mean,
yeah, let's go for it.
Come back some other time and talk. The fact is, if you don't grasp the wave function and entanglement, and then you're not going to understand any of the other stuff about the other interpretations anyway, because they all use the wave function and it always has this entanglement in it. So this is common thread, no matter what approach you're taking. And it is the source of the non-locality and the spookiness of quantum mechanics. So I would love to be able to explain that, because I think it can be easily understood.
Never say easily. All right. I just turned on screen sharing. So
okay. So let me see if I can pull up what I want. This should.
It actually drives me crazy when, I've read all these popularizations now and books with some mathematics in them, and for sort of rookies like me, and so many people say, oh, the mathematics of quantum mechanics is really easy. Conceptually, it's very difficult, but the math is really easy. Well, that hasn't been my experience.
Well, I think the more I'm sorry, it tells me I need to open system preferences to share my screen. I'm just trying to go through. I mean, I have it here, and when I try and do it, it says open system preferences. Okay, I did that. I need to get it to screen share. I mean, the math as math, which is just, as you say, maybe you never learned it, linear algebra, vector spaces.
I did not.
If you're first learning it, okay, it's something to learn, but it's not that high up in the. It's not like if you wanted to understand string theory,
right?
Oh my God, right? It's like that is really, really heavy duty math,
right.
And this it really isn't so much heavy duty math to get up to where you can do quantum theory. Right, let me try this again. I just went through this; it didn't seem to work. But this, I mean, the thing about Bell's inequality, and is that you don't even need that. Okay, right. I mean, what I have said, which is I think absolutely true, is that you can understand Bell's inequality and the total amount of mathematics you have to understand, as we'll see if I can get this screen sharing to work, which I don't seem to be able to, is that you have to know the difference between even and odd. Okay, so if you've grasped the difference between even numbers and odd numbers, you're good to go. And if I can just get this thing, I'm just not sure what I need to do here, because it keeps telling me I need to allow the system to get to this Zoom, and it's showing me the Zoom, and I have it open. It says allow it, and I hope I'm allowing it. All right, let me try one more thing, and if this doesn't work, I think I got it now. All right, good. Oh dear, Zoom us will not be able to record. I don't want to record it. I just want to allow it. All right, I think it'll work now. Let me try. Okay, got it. Excellent.
Right. Yeah, there it is.
All right. So I'm going to go through this argument. This isn't the argument that Bell himself gave. It only was developed later, but it's much cleaner. It's really nice. And so I like to use it rather than Bell's original argument. So, and it's nice just to think about this argument in very concrete terms. So what I've shown here on the screen is an experiment where the little triangular box at the center is producing triples of particles. So you imagine you push a button and one particle comes out of each of these little cannon-like things and heads off in a different direction. Okay? And they head off into 3 labs, which are indicated by those screens. And it's important also that those labs can be as far apart as you like. In theory, light years apart. So far enough apart that you'd sure think what's going on in one lab can have no influence on what's going on in the other lab, right? And when I do this experiment, what I do is I send this particle through a thing called a Stern-Gerlach apparatus, which is just a kind of magnet, and that's indicated by these little pointy and box magnets there. And you'll notice that I have a choice. I can either orient it so it's oriented like this, with the pointy part on top, or like this, with the pointy part to the side. And we'll call this the X direction, and we'll call this the Z direction. Okay, so X, Z. So if I'm an experimenter, I have only one choice. I have 3 experimenters. Each one has only one choice. Do I turn my apparatus like this, or do I turn it like that? Okay? And I press the button. I send these particles out. In their labs, the experimenters make a choice in whatever way they make the choice. It doesn't matter. They can flip a coin, right? They could throw a die. It could depend on the number of shares being traded in the stock market, anything, according to the theory. And now, so you can see that if they just randomly choose these orientations, there are 8 possible global setups you could get, because each one is either X or Z. So you can get XXX or XZX or XZZ, and there are 8 possibilities, 2 to the 3rd. Of those, we only care about 4. And for those 4, quantum theory will make a 100% prediction. So not a probabilistic prediction, but a absolute surefire prediction. So let's just look at the predictions. So here are the predictions. There are 2. If they all happen to be oriented X-wise, then certainly, and I needed to say one more thing. What is the outcome of the experiment? The particle will either be deflected and make a spot in the direction toward the pointy part, we call that up outcome, or toward the non-pointy part, like the one on the left, we call that a down outcome. So we have 2 choices of orientation, and then the outcome is either up or down, depending upon how the particle deflects. It never goes halfway, it always goes one way or the other. Now, what are the quantum predictions? All right, if they're all oriented in the X direction, quantum mechanics predicts there will certainly be an odd number of up outcomes. It doesn't predict whether it'll be 1 or 3, but it does say it'll be odd. It'll never be 0 or 2. All right? So that's pretty clear, right? And it makes another prediction. If 2 of them are Z and 1 of them is X, which is what I had in that picture, then it makes kind of the opposite prediction. You'll always get an even number of up outcomes. It could be 0, it could be 2, it's never 1, it's never 3. Those are the predictions. That's all you have to remember. That's it.
Okay.
Okay? So if you can hold on to that, you've got everything.
Okay.
Now let's remember, these labs are, billions of miles apart. Now the first thing you notice is you say, well, if like Einstein thought there's no spooky action at a distance or something weird going on, one thing that tells us is there can't be anything fundamentally probabilistic here, because once two of these outcomes, I mean, imagine they're all X's, and I know I'm going to get either a 1 or a 3. Once two are fixed, the other one has no choice, right? So if there was kind of coin flipping or some random thing happening to produce this outcome, you wouldn't understand. But how could they coordinate between the three of them to always give you an odd number? If each one's doing something random, how do the others know what this one's doing, right? So the normal thought you have is the only way to explain this without something spooky going on is that they've been pre-programmed. They've sort of made a decision at the source that will guarantee this kind of outcome, right? So what I just gave you is a version of the EPR argument that Einstein gave in 1935. And you see the point of it, right? How could there be anything probabilistic going on if you have these perfect correlations?
Right.
Yeah? All right, so we say, all right, let's take that on board. And now you say, all right, so that's our first conclusion, that all the outcomes have to be predetermined. Nothing can actually happen by chance. So here's the situation graphically and everything, and this is my last slide. And at your next cocktail party, you'll notice this is a cocktail napkin that this is drawn on. So you can impress the person you're talking to with it. And you if you just look at this sort of pretty little diagram, this was invented by David Merman, you'll notice what I've got here is like X1 means the detector in room 1 is set in the X direction, and Z1 means the detector in room 1 is set in the Z direction. Yeah? And similarly for X2, X3. So this dotted line that connects X1, X2, and X3, that represents the experiment where I've chosen, all three X's have been chosen. Yeah? And the solid lines represent the experiments where there's one X and two Z's. So X1, Z3, Z2, X2, Z3, Z1, X3, Z2, Z1. You can just, all those three solid lines correspond to those three possibilities. So now we want to say, all right, what do we want to do? We want to predetermine these outcomes. So I want to put a U or a D in each little circle so that no matter which experiment is chosen, I'll get the right result. And remember, if all three X's are chosen, I want odd. Otherwise, I want even. So let's just try. All right. So I'm just going to, we need odd along X1, X2, X3. It's got to be 1 or 3. Let's just choose 3 because that's easy. So I'll put a U in X1, a U in X2, a U in X3. So if that experiment is done, we're safe. Well, what about Z3 here? I don't know. Let's just choose a D there. Let's put a D in there, and let's see what happens. All right, so I have this line that goes X1, Z3, Z2. That one has to have an even number of U's. That was one of my predictions. The solid lines have to have an even number. So now I'm forced to put a U where I just put it. So I just have one little circle left, but I'm screwed because I need an even number going X2, Z3, Z1, which means I have to put a U, but I also need an even number going X3, Z2, Z1, which means I have to put a D. So I can't put anything in there. Nothing works. Okay? One of the four experiments, no matter how I put in that last one of the four experiments would come out wrong. And now you might say, well, gee, maybe you just did it wrong. And then Merman gives this beautiful argument. It's just absolutely lovely argument. He says, you think you can do that? Can you put U's and D's in these circles so that you get an odd number of U's on the dotted one and an even number of U's on the other ones? And he says, well, suppose you could. Now, pick up the 3 on the dotted one, throw them in a hat. You now have an odd number of U's. Pick up along each of the other 3, right? The next solid one, throw them in a hat, even number. Next solid one, throw them in a hat, even number. Next solid one, throw them in a hat, even number. So I threw in odd, even, even, even. I have an odd number of U's in the hat. But I picked every token up twice. because every of those circles lies on the intersection of exactly two lines. So I can't have an odd number, right? If I picked every token up twice, one thing sure, I cannot have an odd number of U's in the hat. And that's it. That's the proof. That says I cannot predetermine the outcomes of these experiments independently of what experiments are done far away.
Wow, I read, you've got this in your book with this diagram, and the initial diagram that you showed, and to be honest, I sort of tried to understand it, and then I felt like I wasn't getting anywhere, and I moved on, but I understand it now.
Yeah,
I think
it's. I taught this to kind of teenage Buddhist monks in India without much math training, and they got it.
Right.
I mean, it once you see the argument, the nice thing about it is you easily come to convince yourself there's no escape from it. It's not like, oh, it's something's up my sleeve or some subtle ambiguity has come in or anything like that. It can't be done, right? You can't predetermine these outcomes in the right way to always give you the correct result.
Right.
And the only way this can work is that what happens in one lab actually has to depend upon the choices that are made in the other labs, even though they're arbitrarily far away. And that creeped Einstein out, right? And it should creep you out. Right? It creeped me out. That's how I got into all this stuff. Was reading about Bell's inequality in Scientific American in the article that Despagnat wrote in 1979, 80, whenever it was.
I almost hate to ask this question, but what about, is there some implicit insight into the nature of time in this thing? So it seems to me that the order in which the observations are made at the different separated labs must play an important role in the outcomes at the different.
The thing is, and this is why this looks like it conflicts with relativity, which is why Einstein was so upset about it, is that if I make these labs far enough apart, I can do these experiments so that according to relativity, there is no time order. They have no definite time order. They're all at what's called space-like separation, where there's no fact at all about which happened first.
Right.
Okay, that's getting relativity into the mix. Now, some ways of dealing with this, what happens in some theories is that you do need an order. And the order is important. And this is explained in David Albert's book very nicely in Quantum Mechanics and Experience. And if you want to take that route, you have to give up on relativity. You have to say, well, relativity was actually incorrect. You need more structure to space and time than Einstein recognized. You have to go back to something, it's not really going back to Newton, but it's something closer to Newton in order to get the theory to run. Yeah.
Now, is this something that you're sympathetic toward? And the reason I ask is because my impression, right or wrong, is that you like the Bohmian pilot wave model of quantum mechanics, which preserves the idea of particles existing in particular places.
Yeah.
Particles having a real existence as particles, but you say in your book that it's really hard to make the pilot wave interpretation compatible with relativity.
Yeah, that for exactly this reason.
And you seem to be saying, well, and that means maybe that we have to give up relativity.
Sure. I mean, and I think this is a much more reasonable. I mean, think about what was Einstein when he came up with the theory of relativity, with the special theory. He was basically trying to deal with classical electromagnetics. Can you violate Bell's inequality using classical electromagnetic theory? You cannot. And then general relativity to basically come up with a theory of gravity to replace Newtonian gravitational theory. Can you violate Bell's inequality using Newtonian gravitational theory? You cannot. So Einstein was never confronted with having to violate Bell's inequality. And so he came up with a theory that, yes, it doesn't have the resources to do that, but why should it? I mean, it would be crazy for him to have postulated extra structure to space-time that he didn't need. He didn't know he needed. My belief, and this is just a reflection of my respect for Einstein, is that if he had lived a few more years and read Bell's work, and he would have appreciated it, that he would have thought, yeah, okay, maybe I was wrong. I mean, here's a phenomenon I absolutely was not expecting. And that's a good reason to revisit what I did. Because if it turns out to make sense of this phenomenon, you need more space-time structure than I had, okay, that's the way the cookie crumbles. But why should people remain, wedded to relativity, which was developed before any of this stuff was realized? That's what I don't understand. Why isn't this something where people say, well, this is a good reason to go back and rethink what we should believe about space and time?
Tim, let me just, we don't really have much time left. So let me sort of throw something at you and just get your response. So I'm a former English major who's doing my best to try to understand quantum mechanics, and my math is rudimentary, and so I was starting to follow some of the math at the beginning of your book, and then I pretty much gave up at some point. It became too difficult for me, but I'm following your sort of your prose explanations of the different interpretations, the major different interpretations, and I sort of feel like your style of analysis is unsparing. You're pretty ruthless. And by the way, can you
take that down
to regular?
Yeah, let me turn that off. Stop share. There we go.
Yeah. Okay. So I felt by the time you were done with GRW, and there are a couple of different variants of GRW, and then many worlds, and I think your antipathy for many worlds came through pretty clearly, but it's because you pointed out these very deep conceptual problems with it.
Yep.
And then the pilot wave interpretation, which I think you're sort of fond of, but even there, by the end, I felt like you'd shown that each one of these is really problematic in its own way. And they felt like kludgy and ad hoc to me. And so, your goal is to make quantum mechanics intelligible, or at least to show that the project of making it intelligible has made progress. And that we've got, these are like at the very least sort of good starts, and they show that in principle you can have some kind of theory of reality that you get out of the quantum mechanics. But I'm looking at, the best efforts that people have come up with, and we haven't even gotten into stuff like cubism and super determinism and some of these other things that people believe in. But to me, the best efforts look like not very good. And so I wonder, it seems to me a very reasonable reaction to the state of sort of trying to make meaning of quantum mechanics at this point, 100 years after the theory was developed. A reasonable position might be just agnosticism.
Well, I think so the first thing to say is, don't forget the starting point. The starting point is people like Bohr saying, you cannot comprehend this theory. Okay, the reason you can't, you feel like you can't understand it is that you can't understand it. Okay.
Right.
The human ability to comprehend has reached its limits here. And you shouldn't ask for anything more than just this mathematical formalism, right? Now, no matter how kludgy, we could have an argument about how kludgy things are. But no matter how kludgy it is, you understand the damn kludge. You know what's going on according to the theory, right? All of these absolutely refute the kind of counsel of despair that led to shut up and calculate.
Yeah.
And so it tells you there is a project here. Now, if you think they're too kludgy, at least you're saying, well, we know it can be done. Think of these as proofs of concept, right? Here's a way to understand it. Here's a way to understand it. Here's a way to understand it. Don't tell me it can't be understood. If you're dissatisfied with all of them, feel free. Go and see if you can do better. But don't give up on the project.
Here's another possible alternative, and this comes from, and I'd already been thinking along these lines, but this morning I read a blog post by Scott Aronson, the quantum computer guy.
Yeah, I know Scott.
And he let's see, the phrase he used was Zen anti-interpretation, I think he called it. And he's saying that he thinks that it wasn't agnosticism exactly. His point seemed to be that you familiarize yourself with the mathematics of quantum mechanics, and after a while you see all the interpretations as kind of equally valid or invalid or almost irrelevant.
That's look, I'm not sure if Scott was suggesting that, he's just absolutely, and he knows he's wrong about that. If for no other reason, the GRW theory literally makes different predictions.
Right.
Okay. In certain circumstances. And arguably, I'm just actually have been, talking to some people working on this for simple things like arrival times for particles or transit times for particles. In a Bohmian situation, you know what you're talking about, right? Because you have particles. And so, you can go into the theory and say, okay, according to the theory, how long will it take a particle to get from here to here or to go through this potential barrier? In some other interpretations, it's not even clear what question you're asking. So get as zen as you want. You can't erase that difference, right? That's a fundamental difference between working with certain conceptual resources that are provided in some of the theories that are simply not provided in others. And so it's not, no, you're not going to ascend to some, meditative plane where they're all the same. They're just not. I mean, and Scott knows that perfectly well. So I don't know what, I'm not sure quite what he was on about.
I might have been mischaracterizing the attitude toward different interpretations that you achieve once you get to enlightenment. To me, he seemed to be describing something more like habituation. You're so immersed in the mathematics of quantum mechanics as a professional physicist or as a philosopher of physics like yourself that, this hasn't happened to you. Obviously, you're saying, I want to know what the hell this means.
Because I don't have to do these stupid calculations.
Right. Well, I'll just give you another example. I remember I interviewed Murray Gell-Mann in the mid-90s. And, Gell-Mann, this famously arrogant guy. And I sort of brought up quantum mechanics and its mysteriousness and all that. And he goes, what's so weird about quantum mechanics? Quantum mechanics is what it is. And
yeah, well, this was probably before he was pushing consistent histories and stuff. A lot of these physicists who just poo-pooed the whole thing then later turn around and come up with their own pet approach and then try and push that on everybody else, right? Yeah. So it's not really a stable, it is what it is doesn't help you. It is perfectly clear that if I give you a purely mathematical formalism with some rules about how to grind predictions out of it, you can't say it is what it is. It isn't. One thing it isn't is a physical theory, okay? Because a physical theory is supposed to specify what you're postulating is physically real. And the math doesn't do that. The math is not self-interpreting. So
Let me ask you one more question, and then we'll be done. And maybe we'll have to resume this conversation again. But this guy Terry Rudolph,
of PBR theorem fame.
Yeah, I had a conversation with him. So he's somebody who loves foundations. He's really into it. But then he's also trying to create the first workable quantum computer. So my question is, do you think quantum computation, which seems to be, who knows where it's going to go, but there are a lot of really smart people who are working on it. Scott Aronson is also working on it. Scott does care about quantum foundations in spite of what I just said about the Zen attitude. Is it possible that these applications, the sort of power side of quantum mechanics, might yield insights, might be beneficial somehow to foundations, or are those two completely divergent projects?
I would say the only way that stuff would actually be of use to foundations if they suddenly found the computers are not doing what they predicted they would do, and they can't get them to do that. And so what you have is a box where the limits of quantum theory are starting to show up. But if the way they make predictions about what the machines are going to do always turn out to be correct, I don't see that them getting better at making bigger machines is going to help anything, because we know what the mathematical formalism predicts. Right. We know what we expect to have happen. If it happens, that doesn't tell you anything one way or the other about the interpretive issues.
That's interesting.
I kind of doubt it. I mean, what they did, and again, this was Schrodinger was saying entanglement, entanglement, entanglement. And it was only after Bell, for reasons we just saw, that people started to take entanglement seriously. And then quantum computation, quantum cryptography are applications, engineering applications that make essential use of entanglement. And they realize, this is actually just a really powerful physical fact that you can exploit if you're clever to good effect. And sure, but you really don't need more than just the, I need to grind out the predictions part of it to do the engineering. So as long as the predictions come out right, I doubt that will actually be a source of insight into the foundational issues.
I love the idea that the failure of the whole quantum computing project might lead to some big insight in advance.
I mean, you're pushing the limits of how entangled things can get and how much they can maintain their entanglement and so on. Some theories, actually the GRW theory will eventually predict that these computers will break down because, exactly as I said, because they'll have these collapses that would mess the thing up. So there may be a limit to the size of a quantum computer that would come out of GRW theory, and you wouldn't have it in the Bohmian theory or in the many worlds theory. And if you built them that big, you would start to get feedback about which theory is correct.
Oh, that's really cool. I hadn't heard that said about GRW, but I guess it makes sense.
Sure. All the quantum information people assume the wave function never actually collapses.
Right? It's
always Schrodinger evolution, always, always, always. Right. Until they put the thing through what they call a measurement gate. I mean, this is the thing that kills you about quantum computation, is the central problem in quantum mechanics in some sense is a measurement problem, and the way they solve it is by putting a little box in their diagram and labeling it the measurement gate. Oh, here's where we get a specific outcome, right, without any explanation of how that damn thing works.
Okay, I think we're going to have to leave it there. Thanks.
Sure, it was fun.
You've brought me from one level of confusion to a deeper, richer level of confusion.
I hope it was by making the stuff in between clear.
Yeah, absolutely.
So, good.
Thank you very much.
Thank you. That was fun.
Again, one of these days.
Okay.
All right.